Hi, pre-calc students. This is limits day 1. Like I said in my email to you this week, limits is a huge part of the study of calculus. So whether or not you'll be taking calculus as a senior at FHS next year or in college and beyond, you will certainly see limits come up as a huge part of the study of calculus. So it's kind of exciting that we get to spend a little bit of time with it at the end of our course to get kind of a little bit of an intro to get started today. Although there are multiple ways of approaching evaluating limits, we're going to start by looking at it from a table perspective. So what we're going to do is we're going to set up our calculators in just a moment. If you want to find your calculator, you'll need it for this first part of the lesson. And what we're going to do is that this notation says, find the limit as x is approaching 3. That's how I'd read that statement. It's the limit as x approaches 3 for the function 2x plus 1. So you can see we're going to try some values of x in the table, and I've pre-filled in our values of x that I want us to try. I want to get really, really close to 3. And notice how I kind of have this divider in the middle. I want to approach 3 not only from the left-hand side of 3, but also from the right-hand side of 3. And as I kind of squeeze in from those ends and get closer and closer and closer to the middle at x equals 3, I want to know what is my function value getting close to? What does f of x equal? And whenever f of x equals, as x approaches 3, we'll fill that in as the limit here. And I think it will become pretty obvious as to what that number should be. So just as a quick setup on the calculator, I need you to clear out anything you might have in y equals right now. Okay, so go to y equals, and then you're going to type in, first of all, the function 2x plus 1 to get started. And then the important thing that I want you to do is, our table wouldn't have 2.99 as a value. It wouldn't have 3.001. So I want you to go into your table setup, which is second window. So if you hit second window, I want to make sure that your independent is set to ask. And this isn't something we've done it before, but we haven't done it in a while. So make sure the independent variable says ask. This way, when you go to your table, second graph, it should be blank. And you're going to start typing in the values that are listed for x up here, which include things like 2.9 and 2.99 and 2.999. So you can see that the corresponding values for f of x are 6.8. Let's see if I can fill these in. 6.8, 6.98, and then 6.998. Okay, on the other side of the table, we have values like, on the far extreme to the right, 3.1. You could type them in any order, but I'm going to kind of work my way backwards now, getting closer to 3. 3.1 and 3.01 and 3.001 to get things like 7.2, 7.02, and 7.002. So you can imagine if I keep adding on more and more zeros here, or more and more 9s here, that as I approach x equals 3 from the left, and as I approach x equals 3 from the right, we're getting really, 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 really close to a value of 7. So therefore, we say that the limit as x approaches 3 for the function 2x plus 1 is 7. Okay. We're going to try a few more table scenarios, see what we get as results. So if we look at the next one, we're now taking the limit as x approaches 2 for the function x squared minus 3. So you just have to change a couple things here. If you go to y equals, just make sure you change your function. We now want it to say x squared minus 3. And when you go into the table, it's still going to be set up to ask, which is great, but we don't want those values anymore. You can kind of change that quickly by hitting delete. Okay, so if you hit the delete key, you can clear all those out. And I now want to approach x equals 2, so you'll notice how my table's changed to things like 1.9, 1.99, and 1.999. So if I type those in, we get the following values here. So at 1.9, we get 0.61 was the value for f of x. Then I got 0.9601. And then here I got 0.996 in the table. Okay, so that's what was happening as I approached 2 from the left. As I approach 2 from the right-hand side, so again, coming in this way now, getting closer to 2, I'm going to start at the far end of the table, type in 2.1, 2.01, and 2.001, and we'll see that we get 1.41, 1.0401, and finally 1.004. So I think we can say with a fair amount of confidence that as x approaches 2 for the function x squared minus 3, that we're getting closer and closer to a function value for f of x of 1. Okay. You might be able to already predict what's going to happen for the next one without actually filling in the table. So if you think you know what's happening here, go ahead and fill in what you think the limit as x approaches negative 2 is for the function x cubed. I'm going to show you the table and the result in just a moment here. But if you think you've got it, go ahead and hit pause and then take a look at what I have here. So for number 3, the limit as x approaches negative 2 should be negative 8. Now something that I think is kind of interesting when you look at the table here is make sure when you approach negative 2 that you choose values just to the left and to the right of that. To the right of that would be like a negative 1.9, right? Think about what's on the left and right side of negative 2. But I think a lot of you would think that negative 1.9 is really close to negative 2. But if I were to use this as an estimate, and I said, all right, we got negative 6.859 as the value for f of x there, I don't think you would jump to the conclusion that that's negative 8 for the limit. Looking at that, you might say, oh, it's negative 7. Or on the other side, look at negative 2.1 for your value of x. That seems like it's really, really close to negative 2. But using this y value as my estimate, I'm not really that sure, right? I mean, maybe I would have guessed negative 9 for the final limit. So you really, really have to get closer and closer and closer, like super close to negative 2 to see, oh yeah, it really resides probably right at negative 8 there as my final answer. And that's kind of an important concept because I'll tell you that we can evaluate these limits without using a table pretty easily, in fact. So if you haven't caught on yet, I'll explain what we're doing in a moment here. But if you're going to use a table because you're unsure of how to do the limit algebraically, you really want to make sure you're getting super close to that value because even though negative 2.1 and negative 1.9 seem real close to negative 2, I don't know if these values help you to necessarily predict that we're getting closer to negative 8. They certainly don't help you as much as, let's say in the first one, yeah, I mean 6.8, 7.2, I would probably guess the limit in that case was 7. But as we look at a function like x cubed, we're going to see a bigger difference the further we move away from this value that x is approaching. So just kind of a quick thought there. How could we have achieved these same results algebraically? Well, that table that we're filling in, isn't the calculator just plugging in these values of x right here? And these are the corresponding f of x values, otherwise known as y values. So why can't I just, for this example, in number 1, if it's the limit as x approaches 3, plug in 3 for x and find the y value? 2 times 3 is 6, plus 1 is 7. Okay, well, yeah, that was the first answer up here. And then if I take a look at number 2, which is one we just did, limit as x approaches 2, that would be 2 squared minus 3. 4 minus 3 is 1. And what do you know? That was the limit that we found in the table. So I guess it's good that the calculator knows what it's doing. And we can confirm these answers graphically using the table and then algebraically too. Finally, limit as x goes to negative 2. Yeah, negative 2 cubed is in fact negative 8. So I guess that begs the question, then why are we doing this in this table format? Why don't I just plug the number in and get the answer? And I guess the short answer to that is, in a lot of cases, you will just do this. But of course, we're going to come across scenarios where it's not that easy. It might be an answer that we don't kind of expect to happen, or we might get an undefined situation. There's going to be issues that we come across, essentially. So we have to have other strategies like, hey, maybe we'll look at the table, and the table will help us figure it out. All right, let's move on to the other column because we haven't done these yet. Limit as x approaches 5 for this function, negative 3x plus 7. Just a quick plug in here. I mean, this is just really quick evaluating on the calculator or something like that, but negative 15 plus 7 is negative 8 as the answer. The limit as x goes to 1/2 if you plug in a half for all of the x values here. 1/2 squared plus 4 times a half minus 1. I'm going to use the calculator just to make sure, but I feel like it's 0.25 plus 2, 1.25 maybe? I don't know, guys. My math isn't as sharp in quarantine here as I'd like it to be, but I think I'm still pretty good at it. Let's see. Plus 4 times a half minus 1. 1.25. What do you know? Okay. And if you want to write that as a fraction, you could say 5/4. It's really up to you. Okay, I wouldn't mind either way you listed it. And then this one would be pretty easy because just make sure you take the absolute value of -1 plus 3. So 1 plus 3 would be 4. So evaluating limits algebraically, if it's a function we're pretty familiar with and we're pretty confident with that we can just plug in the number for x and go with it, that's what we're going to do. And that's going to be our answer. We are going to take a look at some graphs eventually, actually, not too long from now. So go ahead and turn to the next page. And you'll see on the next page, oops, that's not what I want to show you. We have another table that we're going to fill in. So I know what you're saying, like, Mr. All, why can't I just plug it in and kind of go from there? All right, so let's just play along for a second. Let's go to the table here. We're going to type in the function x squared minus 4 over x minus 2. So if I go to type that in, you have to do one of two things. You either have to make sure that you put parentheses around the top and bottom, or you can do a fancy fraction, right? Alpha y equals gives you numerator over denominator. I kind of like that just so that I don't forget parentheses anymore. But x squared minus 4 on top, x minus 2 on the bottom. We're looking for the limit as x approaches 2. And because I think the last one that I typed into my calculator was x approaching 2. All right, I somehow got these fractions, which I don't want. Let's see. How do I convert these to decimals? I know a way to do that. Let me think. I don't want what on? Do I want classic? Maybe that's what I want. Instead of math print, maybe I want classic. Let's see. Nope, those are still fractions. Huh. All right, something in the mode. We want decimal answers. How about that? Okay, so if you're getting fractions like me, maybe if I change that to decimal, I think I could still do math print then. Sorry, this is taking me a minute to remember how to do. Okay, there we go. We get some nice old decimals there. And sorry if this is a little blurry for you guys. Let's see if I focus for a second. Okay, that might be a little bit better. Anyway, you really want some decimal answers there so we can see more easily. The fractions weren't telling me as good of a story as to what we were approaching here. But I'm going to go ahead and take a look at 1.9. The value is 3.9. And then we got 3.99 and 3.999. And on the other side, coming in from the right side, we got 4.1, 4.01, and 4.001. So I'm pretty confident at the end of the day that the limit as x approaches 2 is 4. Okay, I like that. So then, well, why don't we just do it the algebraic way? I mean, that was the easiest, right? I just go ahead and I plug in 2 for x. So we get 2 squared minus 4 on top, and we get 2 minus 2 on the bottom, right? Just plug in 2 for those x's. Very easy. So we get 4 minus 4 over 2 minus 2, which is 0 over 0. Oh, no. All right, so that's why sometimes a table of values is really useful. Hopefully I've convinced you just by looking at this example. If you went straight to the algebra and you plugged in 2 for x on the top and bottom, you might be looking at this and saying, okay, I don't even know what that means. Is the answer 0? Is the answer undefined? Right? Isn't that what happens when you get zeros on tops and bottoms of fractions like that? I'll tell you, actually, the answer is neither of those two. It's not 0. It's not undefined. In fact, it's 4 should be the answer. That is the real answer. That is the limit as x approaches 2 for this function. And in fact, I don't know if my phone will work, but I feel like I can ask Siri what happens when you get 0 divided by 0. Let's see if Siri wants to help me with that. But let's see. All right. What's 0 divided by 0?
Imagine that you have 0 cookies, and you split them evenly among 0 friends. How many cookies does each person get? See, it doesn't make sense. And Cookie Monster is sad that there are no cookies. And you are sad that you have no friends.
That is kind of sad, isn't it, guys? So 0 divided by 0 is, in fact, something that we can't determine. It's not 0. It's not undefined. There's no way to really mathematically quantify what this means. So Siri is exactly right here, which Siri usually is not very helpful in my opinion, but She's pretty helpful there in saying that this is called an indeterminate form. And what does that mean? It means that if you ever get 0 over 0, you can't determine the limit yet. You can't say it's 0 and you can't say it's undefined. You have to do something else. And actually, oops, I realized that this right here, what is this called? It's supposed to go on this blank. So it says this result algebraically is known as an indeterminate form, which Siri has just told us, because Cookie Monster is sad and Cookie Monster has no cookies. Okay, and no friends, by the way. So how are we going to get 4 algebraically then? Is there a way to accomplish that? And the answer is, of course. We can simplify the expression inside here and then evaluate the limit, because maybe you've noticed that the top is factorable. So if I change this to the limit as x approaches 2 of, the numerator is x plus 2 times x minus 2 over x minus 2. Those x minus 2's cancel out, and this problem turns into the limit as x approaches 2 of the quantity x plus 2. So now if I plug in that 2 for x, I get 2 plus 2, which is my answer of 4 from the table. So have no fear when you get 0 over 0. Sometimes it's as simple as, hey, just factor the top and bottom as much as possible. Once you're done canceling, then you get your final answer. Okay. So what does this actually look like? Because we're going to have to make a big connection between not only what does the limit look like algebraically or numerically in a table, but how can we justify it graphically that this is what it looks like? So we know that this simplifies to this function f of x is the same thing as x plus 2, except we're going to graph x plus 2 as long as x doesn't equal 2. Why can't x equal 2? Well, in the original function, x equals 2 would make this undefined. So although I can factor cancel and get this as the leftover function, it doesn't exist when x equals 2. So we just have to make sure that we don't apply anything at x equals 2. Oh, and by the way, at x equals 2, what is the y value? We just found it. It's 4. So at 2, 4, what are we going to see on the graph? It's been a while, but way back when, we graphed functions that looked like this, and there was a hole in the graph. This is a line that has a slope of 1, so you would just do maybe like a quick rise over run here to get a few other points on the line. Doesn't have to be anything too specific. Okay, that's what the graph looks like. And what you can see is as I approach x equals 2, whether I approach it from the left-hand side of 2 or approach it from the right-hand side of 2, as x approaches 2 from the left and right-hand side of the graphs, what's happening to the y values? They're getting closer and closer to 4. So what's interesting about this is that the limit exists. The limit as x approaches 2 is 4, but the function value, f of 2, has no value at all. So that's a little bit odd. So the function value and the limit don't have to be the same number. In a lot of cases, will they be the same number? Sure, for continuous functions, that's going to happen. But you'll notice in this scenario, those two things actually don't match. Okay. So that's exactly what I'm going to say here. It's a unique case because the limit as x approaches 2 exists, yet f of 2 does not exist. F of 2 is a value of the empty set. And for those of you that